I've been working with inverse problems and tomography in particular for many years. And since 2015, we have been looking at more statistical approaches for these problems, and in particular using machine learning in that context. So this will be the topic for today's lecture. But before we going into the methods and the mathematics, just want to give some motivation behind what I find tomography has been quite important in today's society. In particular, what is tomography then? Tomography refers to a collection of technologies, quite diverse, where there is a common principle, namely that you seek to visualize or recover or reconstruct some interior structure of an object. And you do that by probing the object from different directions either with the particles or with waves. Now this sounds very abstract, but I'll show you in a second more concretely how this plays out. In particular, this can be done in medicine to allow doctors to get a view or visualize the interior structure of the patient or your anatomy. But you could also do it in the context of geophysics or material sciences or in biology or life sciences. And there are further examples here that are listed as application areas. What is common to tomography is that it typically combines mathematics and also lately statistics with physics and engineering sciences. So it's a true interdisciplinary field. So starting with geophysics, even though we are trying to reduce our dependency on oil and gas, there is still, I would say, a sizable activity in finding new oil and gas resources. And one typical procedure for doing that is shown here in this photograph. Here's a boat, and it's towing a bunch of hydrophones after it. These extend for several kilometers long here. And then there's a point source here. There's a source here that is generating shock waves. And this is the aim of this. And this boat is then traveling over the sea surface in a very orderly manner. And the aim here is to find oil or gas. That's oil and gas up to about 10 kilometers deep in the seabed. Now, a more schematic drawing, perhaps is easier to understand what goes on, is the following. Here's this boat again, and here's this thing that you didn't see in that photograph. This is creating an explosion. In part, it creates a shock wave. It's almost like doing ultrasound on the Earth, right? So these shock waves then propagate through the water and finally hit the seabed. Some of them might even go further down into the inside here, but ultimately they will be reflected up. And then what we are measuring here is the travel time it takes for these waves. And of course, to reach each of these hydrophones. And as I said, these are about several kilometers long. So these are quite large measurement setups. And of course, the ultimate goal here is to recover oil or gas cavities containing oil and gas, or ultimately you would say you want to image the seabed, the interior structure of the seabed. Now, reconstruction typically looks like this. These are the few examples where you're allowed to look at it. I mean, this is typically very proprietary data. The oil and gas companies don't necessarily share this stuff, but it looks something like that. And then, of course, it's very difficult for a non-expert to interpret this. You have to be an expert geophysicist. But here you can see the interpretation for the same image here is interpretation here. So keep in mind that this image here, the upper image, is a computed image. It's not something that you measure. This is computed. And then the lower image, schematic image, is the more the interpretation. And this is then the basis for the first test drills that are made. So this is an offshore exploration example involving tomography. You could also aim for looking deeper into the Earth's crust. In this case, you want to do image down to 1,000 kilometers. Now, the aim is not anymore to find any oil or gas or metallic deposits. This is more basic geophysical science to understand how the Earth is structured. Of course, to view that far down, you need a more powerful shock wave. And typically in this example, they had to wait for quite a number of years because earthquakes were providing the shock waves, and those you don't just order. I mean, they happen when they happen, right? And then, of course, you could also do the other version. You could look at the near surface structure of the soil. In this example, one is looking at, this is before doing construction work in Sweden near Göta River or Göta Älv. They are looking at the ground conditions before actually doing the construction work. So these are all examples about using these shock waves to determine what's in the ground. So it's essentially amounts to doing an ultrasound, but we're doing it on Earth. A totally different application, but still the principles of tomography again, is that we are exposing a sample. The aim here is to determine the nanostructure of a sample, ideally down to atomic level. And the sample is typically from material science. It could be some metal or quasi-crystalline material or something like that. And we are using electrons now. We don't use any shock waves. We're using electrons in an electron microscope, which would typically scatter against the sample. So it's an inverse scattering problem. So you want to, from the scattered images, here's typically how it would look like. You would like to recover the 3D structure that is generating these scattered images here. Again, it's a kind of a tomography problem because you're rotating the sample. Yet another example is essentially the same principle, but we're doing it in biology instead. So here we are radiating a biological specimen with electrons, again from different directions, and we seek to recover the internal structure. So typically what you do is that here's an example of an electron tomography, where you have a water solution, and in that water solution are these biological macromolecules floating around, or could be even subcellular components. And those, you freeze this thing in a very clever way, so you form a amorphous thin layer of ice. You put that in the microscope like that, and then you rotate the whole thing, and for each position, you beam it, and then for each position, you gather a 2D image. So you get these 2D projection images, much noisier than what is shown here. And here's an example of a reconstruction then. Here are 2D cross-sections of reconstructions, and here are volumetric renderings of the reconstructed object. In this case, this is the nanomachinery which is driving the flagella of a bacteria. So this is a typical example in life science, basic biological research, how you use these 3D tomographic imaging modalities based on microscopy. Of course, we also want to look inside objects without opening them, let's say in airports. When it comes to security, you're interested in finding hidden objects. So here, typically, you want to do a high-speed tomography combined with typically segmentation and automated classification algorithms. And these are now so efficient that they can actually be rolled out. I think last time I flew was more than a year ago. They had these scanners also for the carry-on luggage at Schiphol Airport. So you didn't have to remove you could have liquids and so on, all in there. And there's also a desire to, let's say, monitor or non-destructive evaluation of, let's say, in this case, this actually is intercontinental ballistic missiles in the US. These things are supposed to be ready 24/7 to be, sent away, hopefully never. And meanwhile, they are in a highly corrosive environments and so on. So you need to check these things from time on and off. And so you're doing tomographic scans on these rockets to see if you can detect certain cracks in the enclosures. And here's a similar thing. This is a valuable violin, and you don't want to crack it open, but you want to look at the interior. Maybe you want to do some kind of interior measurements. So again, the principles are the same. You're scanning it from different directions. And finally, of course, one of the most common applications of tomography is in medical imaging, where the object now is a human being, and you have this X-ray source with the detectors down here, and this thing is rotating, and then you want to recover or reconstruct the interior structure. This is what colored 3D reconstruction might look like. Now, typically, if I just take a projection image, because each of these, let's say, I'm saying that the principle was to probe the object from different directions with some particle or wave. One doing it from only one direction amounts roughly to generating a shadow image of this type. And clearly, this would not be sufficient. So it's quite natural that you would need to have multiple such shadow images from different directions. And of course, the mathematical question is this enough to recover this interior structure? And there is a whole beautiful field of analysis. It's called integral geometry, that is dealing with uniqueness and also even immersion formulas for that context. Just to give you a feeling for tomography, this is exactly the principle again illustrated. So we have this source that is rotating around the red part here, illustrated by the red lamp. In this case, think of X-rays, and the subject here is a human being. And then for each position, we are exposing the patient for these X-rays, and we get this projection image, and then we repeat this from many directions. And from a collection of these, we try to compute the 3D structure. Now, all of these are tomography, and you have seen many examples of tomography now. Are all examples of inverse problems. So what is then an inverse problem? Now, an inverse problem tries to answer the question, what gives rise to observations? So you have observations, you measure something out in nature, and then you ask yourself, what gives rise to these measurements? And typically, you might be aware of the notion of a simulator, where the task is to model something, some complicated phenomena, maybe simplify it a bit. And then when you run the simulator, you're essentially mimicking as if you would be performing the experiment. In that context, you have model parameters that you insert into the simulator, and then you crank the simulator, and out comes data that's been synthetically generated, which is hopefully similar to what you would observe in your real experiments. Well, an inverse problem is to run a simulator backwards. Here, the aim is not to generate data. Instead, we are given data, and we are asking for which input to the simulator that is causing this data that we are observing. And I was just showing you from many examples from imaging, but you can also have any model calibration typically involves an inverse problem. Cryptography is a typical example where the data is the encrypted text. It's supposed to look random, right? And the inverse problem is to recover the source text, right? And so on and so on. So inverse problems pop up in all kinds of conditions in society, I would say. And I've shown you a number of them now from imaging. Now, inverse problems are more challenging than simulation problems for one reason is that they're ill-posed. Typically, a naive way of approaching this will be to say, let's take a candidate model parameter, let's say candidate image, and let's crank this thing through the simulator. So we generate synthetic data with this model parameter at our hands, and then we compare the synthetic data against the observed measured data, right? And then we change this input until we maximize the consistency in the data site. That would be essentially maximum likelihood style estimation. Now, this typically leads to instability, meaning that small changes in the observed data would give rise to huge changes in the solution. So we should not try to maximize this type of data consistency. So this means ill-posedness. The second issue, and in particular this is the case for imaging, is that the problems are large scale. If you digitize an image, then the model parameter becomes an array of the pixel or voxel values. So it's quite a lot of components. And the tomographic data, likewise, is a high-dimensional array. So the large-scale nature of the problem is by itself is also quite a significant challenge. So regularization is the field of mathematics, typically analysis, functional analysis, that deals with handling ill-posedness by balancing the need to fit observed data against avoid overfitting. So fitting the data is taken care of by the data likelihood, which essentially is your simulator. And the prior model is the thing that is trying to avoid overfitting by simply saying that this candidate solution, even though it gives rise to very good data that fits our observed data, it has unnatural oscillations or unnatural features in there. So that's why we should penalize that candidate solution. Now, let's be a bit more mathematical, at least to try to formalize the notion of inverse problem. So the classical formulation is actually not, I would say, almost function analytic, is that we have data is just a letter y. So in tomography, this would be the entire measurement array. And we have the unknown ground truth image, or more generically, the model parameter, x star. The aim is to recover x star, but you're observing the data y. And the relation between the data and the x star is given here. So first you say that y, the data, is a sample of a random variable. And the only randomness in this setup comes from the observation noise. So there's some observation noise, which is encoded by E. So the simulator here is essentially the deterministic component, which is given by what we call the forward operator, which describes how we generate noise-free data, ideal data. So this is the ideal, this is the non-statistical part of the simulator. And then we have some additive, noise term that might be added to the whole problem. And of course, if this is independent and so on, you could do further investigations here. But this is setup. The problem with this setup is essentially that it is assuming that the ground truth image or model parameter is a deterministic quantity. And as such, it's hard to do uncertainty quantification. In fact, if there are multiple model parameters that are fitting the data equally well, we need to, it makes sense to try to model the uncertainty. And that kind of leads us to the need to view the model parameter itself as a random variable. And this leads us to the following Bayesian reformulation of the inverse problem, where again we have the same thing. Where the data is now the same array, but now we say it's a sample of a conditional random variable, where we have the random variable for data conditioned on the ground truth unknown image. If you talk about imaging here, it's the same model, but now x is it's not x star here; it's a random variable x, and then this x here has a prior and is generating x star. And what we want to recover now is the posterior distribution. So in this formulation, this is the Bayesian or statistical formulation. We're not looking for a single model parameter as our solution. That is not a single image, if you talk about imaging. But we're looking at the posterior distribution of all possible images conditioned on the given data or measured data. And clearly, of course, for those of you who have a statistical background, which I think the majority might have in the audience, they would say, okay, in principle, this is a solved problem. You have the Bayes theorem that allows you to express the data likelihood and the prior in terms of the posterior. And that is in fact true. So in principle, this should be somehow a solved problem. There has been quite a significant theoretical development in the field, especially dealing with infinite dimensional models. So where you don't digitize the data and you don't digitize the model parameter here, but you allow them to be typically functions in function spaces. And then there's quite a bit of technical issues popping up, especially if A is a non-linear operator. It might be a solution operator to some partial differential equation or something like that. So but the theory is almost exclusively concerning itself with what happens when the observation error turns to zero. So typically you're looking at how the posterior concentrates around maybe the posterior mean or something like that, and the contraction rates. And there are some quite beautiful mathematics that's been developed I would say the last 10, 15 years, but it's still dealing with this asymptotic setting. I'm going to be more concerned with the computational aspects of this. So I'm not concerned with the asymptotic setting. I'm saying there is the data. I'm given the data. It's not that the data error goes to zero or something like that. There is some observation noise there. That's it. And to give you a feeling for the problem size here in imaging, let's take a look at a standard tomographic problem in medicine. Here, each X element, each model parameter is a function on R3, is a 3D image. And once you digitize this, typically by looking at voxels, you will have, let's say this is a typical problem size. You have 512 cubed voxels, right? So it's about 130 million dimensional array. Likewise, Y is the data. Is a typical CT scanner would acquire about 800 million in this context data points. So it would be 800 million dimensional array. And this operator, this forward operator, in the simplest setting, where you disregard Compton scattering or all kinds of physical phenomena you disregard, then you can rephrase this as a linear operator where you integrate over, you take this X, which is the model parameter, the image, and you integrate it over lines that represents the X-ray lines that you're exposing this subject to. So it's a linear operator. And clearly you see by the problem dimension here, this is a gigantic problem numerically, even though it's essentially will be represented by a huge matrix. If you would even try to represent it, you never try to store it in memory, of course. But nevertheless, talking about the posterior distribution in this context is far, far too complex. So you either have to settle with recovering a suitable estimator, one that is somehow summarizing your posterior will be, the mean is a good starting point, or you might generate samples from it. I want to say something here that an estimator in this context is actually a reconstruction method. So it's not a reconstruction. So a reconstruction would be in the imaging setting, a reconstruction would be an image. It would be an element in capital X here. So something that is approximating X star. But an estimator here is a mapping that goes from Y to X, right? It goes in the reverse direction as A. A goes from capital X into Y. A maps an image into data, whereas an estimator is an operator that maps an element in data space into an element in image space. So it's a reconstruction method. So deep direct estimation is the terminology that, I will have to confess, we made it up for using machine learning or deep learning more in particular to learn the estimator from training data. So I'm restating our problem now. We're not trying to recover the entire posterior distribution. We're aiming for a suitable estimator. Again, Y is a sample from this conditional random variable data given the image, and the image is unknown. Now, there's a quite two natural, let's say, splitting here when you approach this. One is to ask yourself, what am I supposed to compute? And the other question is, how am I supposed to compute it? So the what problem essentially is dictated by the statistical nature of the training data that you have access to and the way that you choose to set up your learning problem, the loss function you choose and how you set it up. So this is essentially has nothing to do with deep learning. This is more related to statistical decision theory applied to signal processing. The how to compute, of course, is once you've done this in theory and assuming that you have access to these old distributions and so on, you of course then realize that this is not the case. You only have this training data. So which architecture you choose for the neural network, which is essentially amounts to parameterizing the family of estimators you're searching over while you're doing the learning, and the actual optimization that is in the basis of the learning itself, which amounts to training the network, which implies that the output is the trained network is the estimator, or approximates the estimator. These are, of course, all related to how you compute rather than what you compute, and they are related to, this is where the deep learning part comes into the game. So by the way, there are references here, and if anybody's interested in the slides, just let me know and I'll make the slides available. At the end of the slides, these references are spelled out. Okay, so I'm just, in the context of tomographic imaging, the capital X contains possible images, 2D, 3D images, and capital Y is a set of or space of possible data. As I said, these are high-dimensional spaces, even after clever digitization. And if you have paired data, that means there are ground truth image and corresponding noisy data, stuff like that, then you can compute Bayes estimators. And for other types of data, there are other type of estimators you could try to compute by appropriately training a neural network. So we're going to focus on the first one. That's what we have time for today, even though we have done the other ones too. So let's move on. I'm going to aim for actually the posterior mean, because that's something that you are one of the easier estimators to have a feeling for. So, and it's also quite a natural, let's say, summary. So we're covering the posterior mean of this conditional random variable, where it's the image conditioned on the measured data, where the measured data itself is generated of data conditioned on the ground truth unknown image. And then there's a relation here between these two. And we're going to do this by learning. And we have this supervised data. So we have these pairs in X and Y that are related essentially like that. They're generated by this pair, this random variable. So first we start up with a theoretical observation that the posterior mean can be written as a Bayes estimator where you minimize the squared 2 norm. So here we break this down. You're looking at the expectation of all possible pairs X and Y. These are is expectation over that. So it's the average error. The error is quantified as a squared 2 norm. R is a reconstruction method, one candidate. You're optimizing over these. It maps data, an element in Y, into an image element in X. So you're optimizing over all possible reconstruction methods, and you're picking the one which on average minimizes the squared 2 norm error. So this is a different way of expressing the conditional mean or posterior mean. Actually, it might be a stupid way if you look at this. It's more computationally demanding. If you look at it, if you would try to do some Markov chain Monte Carlo method or whatever, it will make more sense to work on the right-hand side formulation than trying to go on to the left-hand side. No, sorry, work on the left-hand side, stay on the left-hand side formulation rather than going on to the right-hand side. But we are preparing this for machine learning, right? So we first observe that this expectation, you don't know this expectation because you don't have the joint distribution for X and Y. You might have Y conditioned on X, but you don't have the prior of X, or you don't want to specify a prior. So it's implicitly contained in your training data, but that's it. So instead of trying to handcraft a prior, you replace this entire expectation by its empirical counterpart given by the training data. This, of course, assumes that training data is random draws from the same distribution as eventually the data that you will be applying this thing to later on. And next, also optimizing over all possible mappings from Y to X is a daunting task. So you consider a certain family, parameterized family of mappings, or theta, and where theta is in particular finite dimensional, not low dimensional, but still finite. And then you're minimizing. So this suddenly becomes a finite dimensional minimization. So you end up with an empirical risk minimization problem, a standard supervised learning formulation here. Now, if you would pick as a generic neural network this operator, this parameterized operator here, this is not going to work in tomography. Because in tomographic imaging, if you remember the figures I was flashing you, it essentially amounts to doing this a bit more brute force. You would have 10 to the power 16 dimensional parameter theta that you need to learn. And even though you can maybe handle this in state-of-the-art clusters or high-performance computing environments, there is not enough training data to address the problem in this manner. So it's not feasible for 3D, or not even for most 2D problems either. So here's the key thing there. So what you do is that this parameterization is not a generic neural network, it's something that's domain adapted. And this, we'll come back to that in a second. So this essentially leads us to scientific machine learning. So what is then scientific machine learning? It's I would say it's a fairly emerging field. It's still very much a young field. The concept is, I think was coined towards the end of 2018. It refers to the idea that you have the traditional numerical analysis scientific computing communities that are working with handcrafted domain-specific mechanistic models. And then you have the machine learning community, which is traditionally working with data-driven models that are non-mechanistic, and they're not totally generic. They have, I mean, actually, they are becoming more and more domain-specific also, but still, they are less domain-specific than they are in the scientific community, computing community. So scientific machine learning essentially deals with the idea of combining elements of these two modeling paradigms, which are a bit, kind of contradictory, right? One is saying you let the data tell you what to do, and then the other one is saying, wait a minute, let the modeling guy tell you what to do. So this brings us back to the domain-adapted neural network. So it's essentially when you are setting up your parameterization of the R theta here, we're talking about here, you don't just pick a convolutional neural network or something like that. You pick something which is more adapted to the domain. So you incorporate handcrafted model parameters or criteria or symmetries or constraints into the architecture of the neural network. Now, this is becoming quite a rich domain, I would say. There is, for example, for PDEs, there are several suggested architectures for solving PDEs. So it's not inverse problem. We're talking about solving a PDE. And also for multi-scale PDEs and so on, there are many suggestions now for networks that are designed specifically for that purpose. And I would say also for other problems types that are more and more emerging. So it's definitely an emerging field. For inverse problems, what we want to do is that we are trying to approximate the inverse of A, right? Remember, we're trying to reverse A. We want to find X from Y, right? So we want to put the A inverse is what we want to find. But we don't want to find A inverse because the problem was ill-posed, right? So we want to find a stable approximation to A inverse. So in some sense, we know that our neural network, which is parameterizing an estimator, should approximate A inverse, at least to a certain degree. And A, we happen to know, right? In tomography, it was this linear operator, right? And we can even compute the adjoint of the derivative of A. So unrolling is a technique for doing such a domain-adapted network. Essentially, it's a more general technique to assemble a neural network that approximates an operator defined implicitly by an iterative scheme. That's what unrolling amounts to. So instead of flashing formulas to you guys, I'm just going to show you the idea here with unrolling. So here, the input Y here is this upper left data. This is tomographic data, for those of you who haven't seen tomographic data. And lower right corner is the output image. That's the reconstruction. That's the X star, or an approximation to X star. This is Y, and that's an approximation to X star. Typically, iterative schemes that have been many, many thousands of man-years devoted to this, of devising such clever schemes, is that we want to have some clever approximation of A inverse, where we feed in data, and then there's it kind of essentially uses A and A star, A and A adjoint, and there's a clever updating schemes in between here, and this should go on. Actually, I'm just showing you 3 iterations, 1, 2, and 3, and this should go on, and then in the limit, it should give something sensible. Now, there's no machine learning here, but the idea with the domain-adapted unrolling schemes from scientific machine learning is to replace this updating scheme here with a neural network. So the updating scheme, which is also handcrafted, is replaced by convolutional neural networks. These are all independent. They don't share any weights, for those of you who know machine learning a bit. But the A and A stars remain. That's important. They are not learned or trained. Now let's see how this performs. This is an example of a clinical CT example. The data is 1,000,000 dimensional. The image is 512 squared dimensional. This is the data, how it looks like. It's a lot of Poisson noise here. The whole thing was trained on 9 patients, this neural network. So it's 2,168 pairs of images, 2D images, corresponding CT data. And this is from one of the few public data sets involving CT. And I'm going to show you, this is the ground truth, which is actually the normal dose image serves as ground truth here. We don't want to cut open the patient and look. Here is the tomographic data to the right. So the idea is to go from the right-hand side to the left-hand side. We recover the left-hand side image from the right-hand side. Now, you guys don't know any medical, I don't think you're radiologists, or I wouldn't expect you to be. So I'm just highlighting two regions. The right-hand region, highlighted region, is homogeneous. You want to keep it homogeneous. You don't want to invent structure. And the left-hand highlighted region contains a small feature there that you don't want to wash out. Now, this is this standard, golden standard in clinical scanners. This is what the result you get from this noisy data. You see these streaks here, that these false features, and you have also false features up here that you cannot discriminate from the true ground truth feature down here, or actually it's up here. So a clinician would say that this is a too bad reconstruction, at least when it comes to resolving details of that size down here. So they would ask for more data typically. Well, we're not going to take more data. We're going to throw a machine learning approach to try to clean up this messy image here. So this is a neural network that's specifically trained on the output from the clinical scanners in order to remove the noise and reduce the artifacts. And indeed, this approach came second in 2016 challenge in low-dose CT. And I would say you can see that, but the streak is there. I mean, the PSNR and so on, these are all better for this image. But clinically, not much is gained. The streak is still there. You know, the streak is there, it's not gone. And this false guy up here is still there, right? And the ground truth feature there is almost washed out. So the next image I'm going to show you shows you the effect of including the physics into the neural network. So here the neural network is just used as a post-processing step. So it's totally unaware of the physics of the imaging modality. Whereas in the next step, we're going to show you the physics of when we include the physics. That's it. So you can see how the physics helps in removing these streaks that are non-local artifacts. These are streaks like they're extending here. Okay, and these are also runtimes and so on. But the important thing here is that we actually get a true improvement in image quality, which is clinically useful, not only a PSNR improvement. Let's look now, switch gears a bit, and let's look at using machine learning instead to sample from the posterior, at least try to sample from the posterior. Now, this is a very classical problem in statistics. Sampling from high-dimensional distributions has been around. I would say it's one of the main challenges, or one of the big challenges in statistics, at least in computational statistics. And there has been some inroads into this field also from the machine learning community. And you might have heard about GANs or deep fakes and so on. These are all examples of generative models that are trained by deep neural networks. So the idea in a GAN, the ultimate goal in a GAN is to sample from a high-dimensional distribution, but which is only given in terms of training data. So you don't have any, parameterized approximation of it. And the GAN does this by pitching two neural networks in almost like a minimax game. Well, it's not. It is like a minimax game. One is called the generator, the other one is a discriminator, where the generator tries to generate data that looks like it's been a random draw from a training data set. And the discriminator tries to see if that is a real or synthetic data. At the end of the day, when you're training these two networks that are pitched against each other, you're not interested in the discriminator, at least not in these applications. You're only interested in the generator, because that will then ultimately, when it's trained, will be a machinery to generate data with similar or ideally same statistics as the training data sets. Now, there's a conditional version of this. And then you can also put this in an inverse problems context. That's what we did way back in 2018. And this can then be used to generate, I have no time to go into the math here. It's also quite technical, so I'm skipping all that and say that, it essentially corresponds to a variational Bayes approach, where you learn the approximation to the posterior instead of handcrafting it. And of course, these are competing now with the MCMC techniques in various aspects. I'll mention that if there is time towards the end. So we'll just look at the performance now. So to the left, we have the ground truth, which is a normal dose image. And to the right, I'm not showing you the data now, I'm just showing you the right-hand reconstruction using the standard clinical protocol. This is what you get. You might try to compute, let's say, a maximum a posteriori estimator with a handcrafted prior, a total variation style prior. This is what you get. This assumes sparse edges, okay? But then you can take one sample from the posterior as well. It's quite encouraging, right? It's quite good results. Well, this is a dangerous reconstruction, the one, a single sample, because here it's very clear that what you won't even try to interpret here. You're quite aware of your limitations of what you try to interpret here. But here it's not equally obviously clear. Doctor has to look a couple of seconds to see that certain things in the muscular here don't look natural. So if you create another sample from the posterior, you can create many samples here, especially if it's quick to create them, right? And you see that they are varying here. So obviously a single sample doesn't make sense. So instead, of course, if you can do this quickly, you can compute the posterior mean, right? You get something like that. So now we have computed the posterior mean image, but through a sampling scheme, instead of using a direct estimation by neural network, okay? And let me show you the final example here. So this is a real clinical case. This patient was treated for cancer previously, and then he was referred to the clinic again because he had jaundice, and they were suspecting, let's say, a recurrence of the cancer or relapse, and they wanted to image the liver. So now, of course, now they took a normal dose CT scan of the guy, but to make things challenging for us, we take the corresponding 2% of normal dose data. It's a super low dose data. The data is so bad, well, you see the data here to the left. These are the projection images, the 2D slice projection images, that the resulting reconstruction using the standard clinical protocol is just totally useless. Not even the most seasoned radiologist can interpret what goes on in the liver here. The liver, by the way, is this portion here. So you cannot assess the liver with such a low dose. Of course, they acquired normal dose for this guy, but we'll come back to that in a second. But let's then compute the posterior mean. We apply this GAN trend, they generated from this GAN thing, and then we apply the posterior, we create 1,000 samples, and we compute the mean. Now, I'm running out of time, so I'm going to be a bit quick. If you see this shadowing here, radiologists would react to this. They are quite well-trained eyes. So there is some suspected lesion here. Right? This looks a bit suspicious, this darkening here. But given the data quality, and if you take a look at the clinical protocol reconstruction, you're not really helped much. So I would say it's a fairly obvious question or a valid question. How certain are you that there's a lesion there, right? Of course, you can gather more data, but if you don't want to do that, how certain can you be? Well, we have these 1,000 samples. So why don't we look at the point-wise standard deviation? I mean, that will give us some feeling for the uncertainty. So this is what you get. And you can see, of course, that as you would expect, there's a lot of variation around the bones, where the edges are. But the region where the suspected lesion is not so variable. I mean, there's not so much yellow there and there. So seems to be a little or moderate variability in that region. So that's a good sign. We might maybe trust it. But we can push the statistical analysis even further, I would say. We can even measure the relative contrast in the region of interest and compare that to the entire liver and look at the ratio. And if the ratio is large enough, then we say there's a lesion. And we do that for each of these 1,000 samples. You get something like that, a distribution like that. And based on this, you can design a hypothesis test. If you apply that, it will tell you there's a lesion with a 95% confidence. And of course, this is an example of actually doing a true statistical analysis on the distribution of images. This is actually, we are really working with the probability distribution on images here, or at least the aim is. Well, we can compare now with a normal dose image that was actually taken, and we see that there's this shadowing there. So it kind of gives you a feeling for how these machine learning methods perform. Also, this story has a good ending. This was not a tumor, this was a cyst. So this was not a relapse. So that was also nice to hear. A couple of words about the final words about the computational feasibility and problem size. So again, the images are 512 squared dimensional. So it's 260,000 dimensional images, or dimensional model parameter here. Data is 1 million dimensional. We again train on these only from these 9 patients. So it's not that much training data. I would say only 2,168 pairs. And generating one sample from the posterior. I mean, training takes a couple of days on a high performance workstation, a 4 GPU workstation. But once trained, generating a single sample goes about in 20 milliseconds on a gaming PC. So, of course, the competing approaches from computational statistics is a Markov chain Monte Carlo methods, and there's been tremendous development in that field. We have also experts like Marcelo Pereira here at Heriot-Watt on this topic. And these methods have decent theoretical backing, but they are nevertheless much slower than the machine learning approaches that I'm showing you here. The issue here is that we don't have the theoretical backing in the same way. So it's very much still, we're still exploring this field from a computational point of view. I think I'm out of time. So I thank you for your attention, and I'm ready to also answer for any questions that you might have.